Hello. In these next few videos, we're going to start the move away from purely DC circuits. In other words, circuits in which the voltage and the current are not functions of time. And we're going to start looking at circuits in which the currents and the voltages do change with time. Which is of course much more interesting because most of the circuits that actually do something useful do have currents and voltages that change with time. First thing to do is have a quick revision of capacitors and inductors, because these are the two types of components that get interesting once voltages and currents start becoming functions of time. Here is the hydraulic analogy model that we've been using for a capacitor. It's a barrel with an elastic membrane in the middle of it. Now, if you have this barrel and you have the same amount of fluid, or in terms of the real electric circuit, the same amount of charge in the top and the bottom, then the rubber membrane just exerts no particular pressure in either direction. The pressure in this side is equal to the pressure in this side. We say the capacitor is discharged. However, if we start pumping in fluid on this side of the capacitor, then this membrane distorts. And that pushes out some of the fluid from the other side of the capacitor. In terms of electrical systems, what's going on is we're putting charge onto one plate of the capacitor, and that's pushing charge off the other plate of the capacitor. Once we do that, the rubber membrane starts to exert a higher pressure up in this direction. It's like an elastic band, if you like, pushing up. And that means that in order to get that membrane to distort, we have to raise the pressure of the fluid in this part of the barrel. In terms of the electrical analogy, that means raising the voltage at this side of the capacitor here. So we have a higher voltage here, and we have a lower voltage here. And in the hydraulic analogy, we have energy stored in that distortion of that elastic rubber membrane. In electronic circuits, that energy is stored in the electric field in the capacitor itself, the field between the two plates. Now, the important consequence of this for our discussion of time-variant circuits is that the total amount of charge on this plate of the capacitor, we usually write that as Q, is equal to the value of the capacitance, C, times the difference between the two voltages, the high voltage minus the low voltage. I'll write it as delta V, the difference in the voltages across the capacitor. If I differentiate this with respect to time and look at the change in the charge per unit time, well, the change in the charge on one side of the capacitor per unit time, that is just the current flowing onto the plate of the capacitor. By definition, the current is the rate at which the charge is moving. So I can write this as the current equals C, which is a constant, times the rate of change of the voltage across the capacitor. And that means that we cannot have a voltage across the capacitor that suddenly and instantly changes. It always changes smoothly. If you think about it in terms of the barrel analogy, if we had a sudden change in pressure, that would imply that a whole load of fluid had suddenly arrived on this side of the barrel, and a whole load of fluid had suddenly left the other side of the barrel, just like that, in an instant. And that implies that an infinite rate of flow would have had to have occurred for a tiny period of time in order to make all that fluid suddenly appear in this side of the barrel. And a similar thing is happening on the capacitor. If we did really have a voltage difference which suddenly changed, that implies that we've had an infinite current for a tiny amount of time. And that sort of thing just never happens in any real circuit because no current source can supply an infinite current. The key thing to bear in mind is that you cannot have a voltage across a capacitor that suddenly changes. It's so important that here I've written it in red. It's one of the common mistakes that people make when they start thinking about this type of circuit. A similar effect happens with inductors. You can make hydraulic analogy versions of the inductor with fans and wheels with inertia, but to be honest it gets a bit convoluted and I'm not sure how much help it is. What we can do, however, is go straight to the equation. And E, which is the voltage across an inductor, is L, the value of the inductance, times di dt, the rate of change of the current flowing through the inductor. Now, this means that for an inductor, we cannot have a current that suddenly changes. If you imagine that we had a current and plotted the current against time, if the current did something like this, had a sudden change, that would imply that the rate of the change of current was infinite. The line is going vertically downwards. That's an infinite rate of change. That implies an infinite voltage. And we don't get infinite voltages in circuits very often. We never get infinite voltages in circuits. Once the voltage starts getting above a certain threshold, then some current will start flowing. So, net conclusion, for an inductor, we cannot suddenly change the current flowing through it. The current through an inductor always does something like this. But there is never a point where it does something like that and has a step change. Can't happen. Mostly. We'll come on to an exception a bit later. But it's the kind of exception that only happens with ideal components in simulations and doesn't happen in the real world. So just to show how these two principles work in circuits. If we have a capacitor like this in a circuit and we're just about to switch that switch on, what happens to the voltages at Y and X? Well, without the switch on, then there is no current flowing, so there'll be no voltage across the resistor, so both Y and X would be at 0. As soon as you close the switch, obviously Y will take the value of V. It's directly connected to the positive terminal of the voltage source. But what does X do? Well, we can apply our principles. You cannot suddenly change the voltage across a capacitor. So, if you close the switch at time t equals 0, then Y would suddenly shoot up to a value of V. And it would stay at value of V because it's directly connected to the voltage source. X. Well, if this plate of the capacitor has suddenly jumped up to a value of V, and you cannot change the voltage across a capacitor instantly, then the other plate of the capacitor must have suddenly increased to a voltage of V as well. So it starts up there. The voltage across the capacitor was 0 just before the switch was closed. Therefore, the voltage across the capacitor must be 0 just after the switch is closed as well. And that means that both X and Y have to be at a voltage of V. But then what? Well, you'd now have a voltage across this resistor. There would be X volts across resistor R, which would mean that a current would flow down through this resistor here. And that current would take some of the charge off this plate of the capacitor. That will increase the voltage across the capacitor, and that current will continue to flow through this resistor R until point X has got down to 0, assuming that we've defined the voltage at the bottom of our circuit here as our local reference of 0 volts. So what will happen X will jump up to V, and then it will start to go down. And eventually, after long enough, it will get down to approximately 0, at which point there is no voltage across this resistor, therefore no more current flowing through, therefore nothing changes in the circuit. So we'll get a waveform like this for point Y and a waveform like this for point X. As ever, we can try this on the simulator. I've configured the simulator here with a voltage source which gives a pulse. And I've configured it to be a very slow pulse, so for time below t equals 0, this voltage source is 0, and then it goes up to 1 volt. And then let's see what happens to point Y, which is the blue trace, and point X, which is the purple trace. Exactly as we predicted. Point Y shoots up to 1 volt and stays there. Point X shoots up to 1 volt and then decays back down to 0 again. What about inductors and this circuit? Well, once again, we'll have, before the switch is closed, we'll have no current flowing round this circuit at all. Therefore, there is no voltage across this resistor. The current through the inductor is not changing, it's just 0 all the time, therefore there is no voltage across the inductor either, so both X and Y will be at 0. So if we were going to plot a graph of the voltages against time, for all values of time before 0, the voltage at both X and Y would be 0. Now, as soon as we close the switch, the voltage at Y will shoot up to be equal to V, the value of the voltage source, assuming that we've defined the voltage at this point here as our local reference of 0 again. So Y would shoot up to V and stay there. What about X? Well, you cannot suddenly change the current through an inductor. The current through the inductor was 0 just before the switch was closed, therefore it is still 0 just after the switch is closed. If there's no current flowing through the inductor just after the switch is closed, then there's no current flowing through this resistor either. And if there's no current flowing through this resistor, there is no voltage difference across the resistor. So X would just be at 0. X would start off at 0 just after the switch is closed. While the value of the voltage just after the switch is closed is 0, it is starting to change, because we know that the voltage across this inductor, E, is given by L di dt. And the voltage across the inductor is going to be equal to V, because Y is at V and X is still at 0. So we do have a voltage across the inductor. And that means that we'll have a rate of change of the current, given by E over L. So the current is beginning to increase. And if the current is increasing, then the voltage across this resistor is increasing as well, which means the voltage at X is going to be starting to rise immediately after the switch has closed. It will start to go up. As it goes up, the voltage across the inductor reduces, which means the rate of change of the current reduces, which means that the rate at which the voltage at X is increasing also reduces. So we end up with a curve whose gradient is reducing all the time. But it will keep on going until, after an infinite time, in theory, it does get to the point where there is no voltage across the inductor at all, and therefore no change in current anywhere. And that will happen when X has got to V. And once again, we can see if the simulator agrees with us on this one. Yep, just as expected. Great. Okay, that's the end of this first talk. The two most important things to bear in mind. You cannot change the voltage across a capacitor instantly, and you cannot change the current through an inductor instantly.